Good evening. So good evening. So your discussion is over. On. Can I start? Okay. What? I asked him only. Why you are voluntarily saying I am? Okay. So today we are going to see in the logical family how to realize the logic. Okay. Using a diode, using a transistor, using the combination of diode and transistor and resistors and transistor. Okay. And only with the combination of transistor. Okay. So each means according to the PPT, the advancement of each topic, whatever we are going to see one by one. The starting phase, for example, the starting phase is DL, diode logic circuit, which is starting like phase of development. Okay. So up to we are having CMOS based logic realization. So today we are going to see up to TTL. Okay, transistor logic. Okay. So each logic, each configurations, okay, having its uh, own mainly if you go from top to bottom, okay, it is getting improved, okay, in the terms of speed, in the terms of fan in, fan it, fan out, efficiency, power dissipation, in all the terms, speed, especially speed, okay, how fast your circuit is logically responding, okay. So based on all, we are trying to improve the circuit. Okay, we are trying to improve the circuit. So as I already said that don't use laptop when I am taking the class. Okay. What, you are watching some movie? What you are seeing? I am this much near to you. Huh? Okay. Sorry, any form of addiction? Huh? After attending so many years of online classes. Okay. So first logic is diode logic. So you can see here how we have to form some circuit which will form some logic. Okay, for example, and logic. So the and logic is, if you give the input both low, the output should be low. Okay, if we, in the case like it is a and is a multiplication, okay, logic. So only when both the inputs are high, okay, then only you will get the output high. Either of any of the input is low, okay, your output will be low. That is the logic. Okay. So following the logic, you can see here we are framing the circuit. So we are going to see whether the circuit will work or it will realize the given table or not. Okay, so this can be any voltage. Okay, it can be any DC voltage. It can be any DC voltage. Okay, so we are giving 5 volt. So these are the two inputs we are giving. You know the characteristic of a diode. Okay, this is negative, this is positive. Okay, so whenever you are giving higher voltage in this end, okay, whenever you are giving higher voltage in this end, it will forward bias. Okay, so the diode gets forward bias. It is nothing but a short here. Okay, so if the voltage here is high, okay, so here they have given input as 1, okay, logic 1, but in a diode we will give some voltage, right? If it is 1, we will give 5 volt. Okay, you assume that we are giving 5 volt here. Okay, so what will happen now? This 5 volt will have some, okay, this or you can say that here you are giving 6 volt. Okay, if you are giving 6 volt here, in this end you are giving 5 volt. So positive will have 5 volt input, negative will have 6 volt input. So automatically diode will get reverse bias. Okay, reverse bias means open. This diode, either it will short is nothing but close, otherwise it will be open. So in this logic, if you are giving higher voltage in the terms of 1 here, automatically this diode will get open. Okay, if the diode is getting open, what will happen? Whatever 5 volt you are giving, it will come across here 5 volt. So the your V output will be 5 volt or 1. Logically it is 1. Okay, so only in this case, whenever you are giving both the input higher voltage, then your provided DC input, you will get the output as 1. If suppose here you are giving 0 volt and here you are giving 6 volt also, what will happen? This will become short. Okay, this will become short circuited. So automatically this 5 volt will flow here. Only possibility when the 5 volt will flow through across this diode DL. Okay, across DL the diode, okay, will when this diode will conduct, when the diode will forward bias is at the condition 1 1. Whenever you are giving in the A and B terminal some voltage greater than your bias voltage, at the time only your output will be 1. Okay, so this is a configuration we are trying to realize an AND gate. You can also realize a AND gate, OR gate or any gate by connecting the diode and this resistor combination in a different aspect. Okay, you can realize this your diode logic for all the gate. Okay, one of the example whatever we are seeing is a for an AND gate. Okay, so only if you give 1 here, so again I am saying this 1 is nothing but high. Okay, 1 means high means 6 volt. Okay, you take 6 volt, 6 volt. Okay, if you give 6 and 6 volt, automatically what will happen? Okay, this it will become what? Open circuit. Okay, open circuit means this got braked. Okay, so directly this 5 volt will appear across this. So it is having a loss of 0.7 volt. Okay, minus 0.7 volt. So your V output will have a output of 4.3 volt, which is also high. Okay, 1. Remaining all the condition, either of these two diode will get shorted. Shorted means this 5 volt will flow across here. Okay, so the logic will be 0. If you see V out, other than this condition, okay, remaining all condition, the V out will be 0. Okay, so next is resistor transistor logic. The output voltage drops about 1 volt when the fan out is 5. Fan out, fan in explanation we have seen. Fan out is nothing but how much load you can connect when you are connecting a logic circuit. Okay, so the power dissipation will be generally in 12 milliwatt. Okay, and the propagation delay will be 25 nanosecond. Okay, so these are the advancement when compared to your previous, okay, circuit. Okay, the name is resistor transistor logic. Using that we are realizing a NOR gate. Okay, so the name itself saying it's a combination of resistor and transistor. So we are employing two transistor T1 and T2. Okay. So transistor also having a logic. Okay. What is the transistor logic? Transistor can operate in a three region: cutoff region, saturation region, and active region. But on means saturation region, off means cutoff region. Okay. So using this, we are going to play from the circuit only. You can say that. Okay, from the circuit only you can say like this. Whenever this 3 volt, okay, whenever this 3 volt is appearing across here, your output will be 1. Remaining all condition, your output will be 0. Okay, so when this 3 volt will appear here, when this T1 and T2 became open circuit, right? When you will get 3 volt in your output, whenever this T1 and T2 get open circuit, because whenever it gets short circuit, the 3 volt will flow to the ground. Okay, so you should avoid the voltage flowing through your transistor to ground. Okay, so when you can avoid, only if you open circuit or you open your transistor. Okay, opening a transistor is nothing but what? Cutoff region. Okay, when the transistor, we can say it is open whenever it is in cutoff region. Okay, if you are not giving any base voltage, okay, you are not giving any base voltage, then the transistor will be in the cutoff region. If you start giving IB value, yesterday I have drawn a characteristic of output characteristic of transistor. Okay, so whenever you are giving IB 10, 20, 30, accordingly the IC current also will increase. So same way here also, whenever you are giving some IB current, automatically it will give, anyhow IB is based on your V in and V in B, A and B. Okay, here how much you are giving, even you are giving, you are biasing here. When the switch, okay, when the switch started conducting, it will go to ground. Okay, if it goes to ground, then VO became 0. Okay, our output became 0, these conditions. Okay, so if you see here, either one of the transistor is attaining cutoff region also, it will get grounded. Okay, either T1 or T2, any of these two getting started conducting, automatically your VCC will get grounded directly. Okay, means you won't get any output. Whenever these two transistor T1 and T2 both are open means what? When both are in cutoff region only, you will get some output in your circuit. Okay, so same concept only. So I'll write the logic now for one case, so you will understand. Okay, so for example, if this transistor is conducting, okay, I am giving a 3 volt. Okay, this transistor is conducting. Okay, means, sorry, we'll see first condition. Okay, whenever I am giving 0, okay, whenever I am giving 0 means when my base current is 0. Okay, whenever my v in at B terminal also, IB is 0. So what will happen? You are not giving any base current, both transistor will go to cutoff region. Okay, cutoff region means what? I already said that cutoff region is nothing but your transistor is open. Okay, saturation region, your transistor will conduct or conduct. You take conduct. Okay, your transistor will conduct. So when both are cut off, so directly your 3 volt, okay, will get grounded by both the transistor. So if you see your V0, it will be definitely sorry, both are in cutoff. Okay, if both are open, cutoff is nothing but open. Okay, if both are open, automatically this 3 volt will flow across here. Okay, so your V naught will be 3 volt, which is nothing but high. Okay, high or 1. Remaining all the 3 condition, either T1 or T2. Okay, any of the one of the transistor will conduct. Okay, if you give V in 0, second condition, if you give V in 0 and V in 1, okay, you are giving some voltage in here, this will conduct. Okay, if this conducted, this 3 volt will flow here to the ground. Okay, similarly, if this is not conducting also, this will get grounded. Okay, so all the condition apart from the first condition, you will get the output as 0. Okay, so next is a combination of whatever we have seen in the last 2 example. Okay, in the resistive transistor logic and before diode logic, in both the logic we are combining. Okay, if you see here, this is diode logic. If you see here, this is resistive logic. Okay, so this resistive logic, what we have seen, whenever your transistor is conducting, okay, whenever your transistor is conducting means high. Okay, your output is low. That only we seen in the last example. Okay, similarly, whenever your transistor is low, means whenever your transistor is off, your output will be high. So this indicates which gate? It's a NOT gate, right? Whenever your transistor is conducting, whenever your transistor is in the high state, your output is low, because there, whenever your transistor is conducting, it got grounded. Okay, so similarly, whenever your transistor is not conducting, okay, automatically your output became high. So it means that it is NOT gate. Whenever you are giving input 1, you are getting output 0. Whenever you are giving input 0, you are getting output as 1. NOT gate. What is NOT gate? We will say inverted gate. Okay, you give input 0, it will give output 1. Okay, so we know that this circuit is giving the output of which gate? AND gate. Okay, so AND gate, if you are connecting with NOT gate, what will happen? If you connect on AND gate with a NOT gate, what will happen? AND connecting with NOT. So it means what? Which gate? NAND gate. Okay, so that only this. You can see here, now we have realized the NAND gate. Simply we have connected with one transistor circuit. Okay, I said this circuit is a inverter. Okay, so simply it will invert and give the output. Okay, so that this only explained here. Okay, so you can read. So this is modified diode transistor logic. So previously what we have seen, this circuit are having more components, okay, more losses. So how many diodes we are using here is almost 3 diodes we are using. Okay, each diode will have a drop of 0.7 volt. Okay, so to avoid it, we are going with the configuration. Initially we are connecting this with one transistor, then we are connecting with diode. Okay, even transistor will have a drop, transistor also will have a drop of 0.7 volt. But this configuration, they are saying that fan out capability means how much load you can connect, that can be enhanced. But if you see, since we are using 2 transistor, 3 diodes, you will have more losses only. But one of the advantage of using this is, anyhow we are realizing the logic, so we can connect more fan out. Okay, you can have more output from this. Okay, more load, higher configuration load you can connect. Okay, next is TTL, transistor logic. Okay, so transistor logic means this logic is between transistor and transistors. Okay, so what is the disadvantage whatever we have seen in the resistive transistor logic or in the diode transistor logic is, for the resistive transistor logic we has a very poor noise margin. Poor noise margin means it will easily change its state if it get any disturbance, if it get any noise. Okay, if some noise come, automatically instead of showing high it will show low. Okay, so it's very prone, like we can say very prone to noises and disturbances. Okay, so poor fan out means you cannot connect a high load in the end of the transistor, this logic. Okay, so low speed, the speed of logic means the in the terms of nanosecond or microsecond it will get delay. Okay, how high power dissipation. Okay, we are using resistance. Okay, we are using resistance, so what will happen, it will dissipate more power. So next logic is diode transistor logic, which is like whatever we have seen up to now, that is the best. Okay, but still it is having two advantages. One is low speed. Again, the response of the logic is little low, and it having a improved noise margin. Okay, improved noise margin means one of the disadvantages of RTL is it is having an issue with the noise, but when compared to RTL, this DTL is having little more better noise acceptance ratio. Okay, it won't change the state. Okay, so next for so previously what we have seen in the diode transistor logic, we had one of the main disadvantages is speed. So this transistor logic we can improve the speed. Okay, so how we are improving, we'll see the origin of TTL gate was slightly improved over DTL, and you can see that it was introduced in 1964. 1964 means around how many years, 40, 60 years before, 60, yes, 60 years before whatever they invented we are studying now. So TTL has but these all are basic, as I said, only if you know the basic, even it is 60 years, 100 years. Okay, you can you want to invent something, you want to manufacture something, you want to have some idea, from here only it will start. Okay, so transistor alone perform the logical operation, and here the logical operation is fully taken care of transistor, no diode or nothing. Okay, so transistor only will take care of everything. Transistor will operate in the saturation mode and cutoff mode. Okay, that we have seen, cutoff and saturation mode. So transistor of the saturation, so saturated, sorry, fastest of the saturation logic family. So it will be fast. Okay, as I said before, the disadvantage of the previous case is very slow. It will be fast and low manufacturing costs. Okay, and available in small scale integration chip and medium scale integration chip, and relatively but when compared to other thing, it is high power consuming. Okay, so because here we'll see we'll have multiple emitter terminals. Okay, so TTL subfamilies are standard TTL, high speed TTL, low speed TTL, sorry, low power and Schottky, and low power Schottky TTL, and fast TTL. So this comparison we have seen in the last class, last PPT they have mentioned. Okay, so the comparison of the speed and everything, last PPT, previous. Okay, three different types of output configurations are open collector output, tandem pole output, and three state output or tri-state output. Okay, so generally a transistor operation, how it will be explained, we already know. Okay, no need to know, we can directly go to TTL configuration. So this is TTL. Okay, so this TTL we are going to perform the AND operation. See here, we are replacing our previous diode configuration with our transistor. Okay, so you can see here we are having a multiple emitter here. Okay, this is emitter. We'll have multiple emitter. Okay, not single emitter. We'll have multiple emitter here. So the tandem pole, what they are saying means the configuration how we connected. Okay, these two transistor. Okay, so this is tandem pole. So they are splitting this into three stages. One is input stage, next is phase splitting stage, and third is output stage. But if you see very simply what it does me, what it does means, okay. So whenever you are giving a, what is and logic? Whenever any of the input is zero, the output will be zero. Okay, that only no. So 1 minute. See here here we are giving 5 volt. Okay, whenever this transistor, whenever this transistor is conducting, okay, whenever this transistor, if you are giving some emitter input, okay, so here A B combination, so I am writing AND gate A B and output. Okay, so 0 0 0 0 1 0, okay, 1 0 0 1 1 1. Okay, this logic, this circuit should perform. Okay, so here in AB I am giving 0 0. Okay, if I give in emitter 0 0, okay, what will happen? This transistor won't conduct. Okay, this transistor won't conduct. So what will happen? Automatically that this 5 volt will get grounded. Okay, so your output will be 0. Okay, similarly if you give the next condition 0 1, again one of the input to the transistor is 0. Okay, emitter input is 0, so automatically again this transistor won't conduct, again it will be 0. Okay, so only whenever you are giving one input as 1 1, this transistor will conduct. When the transistor started to conduct, only it will give to the Q2 input. Okay, from here you will get the output. Okay, this output will appear across your output Y. Okay, so that is the logic of this tandem pole output transistor. So they have shown that instead of transistor, they shown that if you are using a diode, how the logic will work. Okay, this is for I think NAND gate. Okay, this is they have given for AND gate, and this is two input AND gate. Okay, so it is like they have shown that input condition A or B or both are low. Okay, the transistor will get on reverse, AND gate reverse. If you follow this configuration, okay, whenever in any of, okay, your A or B, any of the A or B or any of one of the thing is getting, you are getting low input, automatically your output will be high. And whenever you are giving AB high input, your output condition will be 0. Okay, so it is like your previous logic. Okay, here you are giving high voltage, here also high voltage is there. Okay, if both are, you are giving high voltage, so what will happen? Automatically it will go to ground. Okay, whenever any one of the output is low, so this ground will be avoided, automatically the output will be coming through your this diode. Okay, this is for NAND gate. Okay, so that is the concept. Okay, so either you can make a AND gate or NAND gate by connecting at only transistors. Okay, Three state I will explain later. Okay, so